Okay, so just like we did with exponential functions in exponential functions and equations in Unit 7, we're kind of following the same pattern with logs, except first we had to understand what actually logs were. Then we talked about the graphs of log functions, okay? And now we're going to talk about logarithmic equations, which oftentimes could be exponential equations, because remember, I can write equations in either this form or this form because these two are inverses of each other. So remember just what I talked about, the restrictions, okay? When you solve these log equations, you do have to state the restrictions. And remember, if we're taking log base b of x, I already used this word before, we call x the argument. And I said x has to be greater than 0. Can't be 0, can't be negative. The base, log base b, also has to be positive. Okay? And b can't equal to 1 because that just doesn't make any sense. So we've got sort of two situations with log equations here. One, and here's an example of each. We've got equations where only logs appear with the same base. This is an example of this one. We've got logs on each side of the equation. The second type is we've got a log on one side and a number on the other, or a constant on the other. So this would be an example of the second type. Well, pretty straightforward. Remember when we solved exponential equations, if we got the bases the same, we just cross them out and solve what's left, right? Same with logs. So here, we might as well go ahead and do this one, even though it's the second one. First of all, what are the restrictions? X has to be greater than what? -1? -4. Because I've got a single log on each side, all I do is just cancel out the logs and solve what's left. X plus 4 is equal to 11. X is 7. That's bigger than -4, so that's a good solution. Okay. If you have a log on one side and a constant on the other, you change it to exponent form and then solve it from there, after stating the restriction. So what x has to be greater than what in this one? 0. Because there's no log, because we don't have the same logs on either side, we can't cancel them out. So we're going to change, that means 2 to the third equals x. That's how we change from logarithmic to exponential form, and we've got a pretty easy equation left to solve. All we have to do to find x is do 2 to the third. That's 8. That's it. Okay. So those are just to kind of get you used to it. Now we'll get a little bit more complex. Is this type 1 or type 2?
No, type 1.
Type 1 because it's not constant. It doesn't have logs on both sides. And it doesn't matter if I move a log over here, there's still a constant there, so I can't just cancel out the logs. But I could do something with this. Oh, sorry. Restrictions first. For this one, x has to be greater than
0.
And for this one, x has to be greater than, so I take the higher one. Like even though one would work here, one would not work here because it's negative. So I have to go greater than 3. Can we simplify this? Can't we combine them into a single log? What do I do with the arguments? X times x minus 3 equals 1. Don't forget, if there's no base written, we assume it's 10. We can even go further and multiply the two, get x squared minus 3x. And now we change to exponent form. So this becomes the base 10 to the first. 10 to the first equals this expression. So 10 to the first equals x squared minus 3x. What kind of equation do we have? A quadratic, a squared one, right? And how do we usually solve those ones? Factor. You got to bring everything over to one side and factor it, and then solve from there. So I'm going to bring the 10 to the first is just 10. So I'm going to bring this over here by subtraction. So I'm going to get 0 equals x squared minus 3x minus 10. I have a trinomial. This is pretty standard factoring. Negative 5 plus 2. Therefore, my solutions will be the values of x that make each of the factors 0. Are those both okay? Check them against your restrictions. Negative 2 is not okay. It has to be bigger than 3. So always check them against your restrictions. So there's only one solution, and it's 5. What's the restriction here? Greater than 3, because I have to take the higher number. This one's greater than negative 2. This one's greater than 3. You have to take the higher. Well, I've got logs everywhere. All the terms are logs. So as long as I can get a single log on each side, I can cancel them out. Well, I can simplify this to a single log. It becomes log base 4. What do I do with the arguments? Divide them. And now the log base 4s can go, and I solve what's left. How do we solve this? Yeah, can't we? It's a fraction equation, so I want to get rid of the denominators, times this by x minus 3, which means I got to times this side by x minus 3. So I'm left with x plus 2 is equal to 6 times x minus 3, which is 6x minus 18. Get the x's on one side, so I can bring the 6x over here, make it negative 5x plus 2 equals negative 18. Take the 2 over to the right, so I get negative 5x is equal to negative 20. And x will equal What will x equal? 4. Good solution? Yeah. Straight and straight. Okay. And that was a number 2 type, by the way. Get a single log on each side and take them away. Okay. Couple more and then just throw a couple little ones at you after that. Restrictions on this one? X has to be greater than -2. I've got a constant of -1 there, which means I got to get the logs on one side, the constant on the other, and then get a single log on get a single log on the side where the logs are, change it to exponent form and solve from there. So I'm going to take this over here by adding 1. And I'm going to take this log 50 over to join the log on the left by subtracting log 50. So I'm going to get log x plus 1 minus log 50 equals 1. What? Oh, gee. What am I doing? I don't know where that came from. Equals 1. Well, I can compress this into a single log. It would be log so it'd be x plus 2 divided by 50 equals 1. Well, I can't go any simpler, so now I have to change to exponent. Remember, there's no log base, so we assume it's 10. Therefore, 10 to the 1 equals this whole expression. So 10 to the 1 equals x plus 2 divided by 50, or just plain old 10. What are you going to do to solve? Times 50, both sides. So I get 500 is equal to x plus 2. It's a pretty big number, our answer, but that's allowed. 498. And the last one of these examples, well, first of all, the restrictions, there's only one variable over here, so x must be greater than 0. It's an equation where there's all logs. So if I can get a single log on the left and a single log on the right, go from there. Well, it doesn't look like there's anything to do on the right. There's nothing to combine, no log law to use, but I've got some stuff to do on the left. What are we going to do first? Deal with those first. How do we change those? Drop it in front. So this is the same as log base 4, 2 to the 4th, minus log base 4, 4 to the 1/2. Okay, you have to do the power law first before we can combine them. You can't have anything in front before you combine them by multiplication or subtraction or addition. Well, I know what 2 to the 4th is. 16. And I hopefully know what 4 to the 1/2 is. 2, because it's half the same as square root. Equals log 4x. Now I can combine these into a single log by doing 16 divided 2, which is just plain old 8. Take them out. I got my answer. Okay. Okay, the last two. You might have to do some thinking. Notice that this one is actually an exponential equation. There's no log, well, there's a log in the exponent. So I guess it's a log function within an exponential function. What would you do here? What do you think you would do here to try and figure out what x is? I mean, 7 to the, what's that? I thought I heard somebody say something. No, just me hearing things again. Not that old. Well, we change it to log form. See what it looks like. What would this look like log form? Log base 7 of x equals log base 7 of 2. Right? This becomes the base of the log. This becomes the argument. This is what the log equals. So log equals log. What's x? 2. How about this one? Well, I mean, I could go try exponent form. Exponent form is 5 to the x equals 40, but I don't know what 5 to the what equals 40 is. I mean, I know 5 squared is 25. 5 cubed is 125, so it's 2 point something. So that really doesn't help me. Didn't we learn actually how to calculate these things on our calculator? How would I find it? Log 40 divided log 5. So you're going to have to use your calculator for this one. You could have actually used your calculator for this one too. You could have changed this to a decimal and then done 7 to the whatever that number is, you would have got the same answer. Okay. But just remember, if you get somewhere like this, you can always use a calculator for it. And I'm not sure what exactly that works out to. 3 decimal places? Anybody got it? 2.9? Read the whole thing for me. Read the whole answer for me. 3 decimal places.
2920.
Okay, sorry. I thought you were saying 2.9.
No.
Okay, gotcha. We're good. Now, Wednesday, we'll take some more log equations up, but these ones we're going to have to use our calculator for, and these ones do get a little bit more involved. So we'll be able to finish that this week. We'll be able, next week is going to be bad. Because, I don't need to record this.